Okay, the next problem I want to do for you is a mixture problem. There are all kinds of mixture problems in all kinds of different situations. You'll use this a lot in chemistry. And when you do a mixture problem, sometimes it's a good idea to make a table. You don't have to, but it's never a bad idea. And sometimes in mixture problems, you'll actually use more than one variable, and it is possible to do that. We're going to try to do it by defining one unknown quantity in terms of the other, because I want to stay consistent in how I'm solving these. But I just want you to be aware that there is more than one way to do it. So the first thing I'm going to do is, well, after I read through the problem, which I'll let you read through it on your own because you have the notes, I'm going to make a table. So let's use some magic here and make a table. Okay, see how magical that is? When you make a table in these mixture problems, a lot of times you will have columns for the quantities and a column for the totals. And then the rows will be rules or pieces of information. So I will have a column for the $2 candy, and I will have a column for the $5 candy. Let me kind of give you a little bit of background on this problem. We have two different types of candy, two different products. One's expensive, one's cheap, and we're trying to mix them together. But because we're nice, we don't want to change the value of what we're creating. We don't want to charge more for the combined stuff than we do for the individual parts. Now, in the real world, that's usually not the way they do it. Like if you go to the store, a lot of times you'll buy bacon or you'll buy filet mignon wrapped in bacon, and they will charge you, more for that combined product than they would individually. And the reason they do that is because if they wrap the filet mignon in bacon, filet mignon's like $15 an hour, and bacon's like $2 an hour, so that way they can charge you $15 an hour while they're weighing the bacon. So you'll get kind of this information from me as we go along, because I used to run a supermarket years and years ago, so sometimes I like to share that little practical stuff. So if you buy filet mignon, don't buy it when it's wrapped in bacon. But a lot of times stores will do that. They'll take a product and they'll add something to it or change it and then charge you more for it. It's called upselling. And I guess it's not a terrible thing because they're adding labor to it, but you just have to be aware that you're paying more for stuff. Okay, so anyhow, back to this problem. I have a $2 candy and a $5 candy, and I have totals. And often the rows involved here will be the amounts and the values. Not always, but often that's how your rows look for mixture problems. So for this problem, I want to mix a certain amount of the $2 and a certain amount of the $5. I don't know how much of the $2 I have, so I'll call it X. It says I want to make 50 pounds total, so it'll be 50 goes there. And then if I want 50 pounds total and X of the 50 pound, X of the 50 pounds is the $2, how much will be left for the $5? Well, 50 minus X, I should say. So if one quantity is X and both quantities together have to add to give 50, then the other quantity must be 50 minus X. Like if one quantity was 30, the other quantity would be 20. You'd get that by subtracting. Or if one quantity was 10, the other quantity would be 40. You get it by subtracting. Well, if we don't know the first quantity, we call it X. The other quantity will be 50 minus that. Okay? Now, what is the value of this candy? Well, the value of 1 pound would be $2, but we have X pounds, so the total value is 2X. The value of 1 pound of the expensive candy is 5. So if I take all of the pounds, it's going to be 5 times 50 minus X. Make sure you put that in parentheses. What's the total value? Well, I want my total value, I want to sell it for $3 per pound, and I want 50 pounds. I know some people are probably saying, why don't you just write 150? Well, that's so if you look back at your notes later, you'll know where that's coming from. Okay? So now, when you do a mixture problem in this way, the top equation, if you add these two columns, you should get your third column. So that's kind of a nice check that you're on the right track. So x plus 50 minus x equals 50. That's a true statement. It's not as helpful as the second equation, even though it's a nice check. The second equation, and I said equation because that's what these rows end up being. They end up being the equations in our problem. So here is my equation that's going to help me solve this. And I'll write 150 now because we know how to multiply 3 times 50. And then I distribute, just like we did before. I get 2x plus, this is going to be 250 minus 5x equals 150. 2x minus 5x is negative 3x. And then if I subtract 250 from both sides, I get negative 100. And then divide by negative 3, I get x equals 33.3 repeating. So you have to add 33.3 repeating pounds of the cheap candy to get the mixture that you want. The expensive candy, how much of that are you going to add? Well, so let me put pounds here too. The expensive candy would just be 50 minus 33.3, which when you do 50 minus 33.3, you're going to get 16.7 pounds after you get done rounding. I guess we should probably round this to 33.3 since you really can't do 3 pounds unless you have a really accurate scoop when you're scooping the candy out. Now, this problem, the way we solved it, looked a lot like our investment problem because really the investment problem was also a mixture problem. We had a certain amount of resources we wanted to go to one thing and a certain amount we wanted to go to another. We had an amount of money we were investing and we had a value of the interest. So this problem, very similar to the one we just did.